Picture this. You see someone playing the drums, right? The sticks hit the cymbal, and instantly your brain connects that visual, that strike, with the sharp ringing sound. It's something we humans just do, effortlessly, linking sights and sounds.
It really is second nature. We don't even think about it.
Exactly. Okay, let's unpack this, though, because what if I told you that AI is now learning to make these same kinds of connections, figuring out which sights and sounds belong together, but without us having to, painstakingly label everything for it?
And what's fascinating there is how different this is from, well, how we've typically trained AI.
Right.
Traditionally, if we wanted an AI to get that a picture of a dog goes with barking, well, you'd need countless labeled examples.
You'd have to tell it, this is a dog, this is what a dog sounds like, over and over.
Exactly. You're explicitly teaching the association.
But today, we're diving into some really interesting work. It's coming out of MIT, and it's kind of changing that whole paradigm.
It is. They've developed a new way for AI to learn these audiovisual links, all on its own, just by observing.
So our mission in this deep dive is really to explore this new model. It's called CAV-MAE Sync.
Right. We want to understand the clever way it learns, what makes it different, and, crucially, why this kind of self-supervised learning could lead to some surprising applications, things that might actually affect you.
And to get there, we've got two key sources lined up. There's a recent article from MIT News, gives a great overview, and then the original research paper itself, which gets into the nitty-gritty.
Yeah, the details are fascinating.
Yeah, this is the part I'm particularly curious about.
Oh, but before we really jump in, just a quick note for you listening. If this whole world of AI intrigues you, and maybe you want to deepen your own understanding, RajManikabam.com offers a really comprehensive AI course. And you can use the discount coupon code QPT at checkout to get a special discount.
Nice. Okay, so promo done. Let's get back to it. We started by thinking about how naturally we connect seeing and hearing. Guitar strummed, we hear music. Automatic.
Right.
But how have we actually taught AI to do something similar up until now? What was the old way?
Well, like we touched on, it heavily relied on that explicit labeling. Think of it like for every video clip and its sound, a human provides a tag.
Like cat meowing or car driving by.
Exactly. The AI then learns to map those specific visual patterns to those specific sound patterns, all based on the labels humans gave it.
It's like showing a kid flashcards, right? Picture on one side, word on the other.
Good analogy. Yeah, it works, but think about the effort involved. Creating all those flashcards, all that labeled data, it's a bottleneck.
A massive one. Which raises the question, couldn't we teach AI more like a child learns? By just watching and listening without needing constant instructions.
And that's precisely the challenge that Edson Araujo, Andrew Rudachenko, and their colleagues at MIT and Goethe University tackled with CAV-MAE Sync.
CAV-MAE Sync.
Yeah.
Okay, it sounds like a pretty big step. What's the core innovation, the big change in how this model learns?
The real breakthrough is that CAV-MAE Sync learns to align audio and video data directly from unlabeled videos. It doesn't need those human-provided tags.
Wow, so it just watches and listens.
And figures out for itself which sounds likely correspond to which visual events. The MIT News piece really highlights this, that the ability to learn without guidance opens up some really exciting possibilities.
Okay, give us some concrete examples. Where might you actually see this tech being used?
Well, think about journalism or maybe film production. You've got hours and hours of footage.
Right.
And you need to find, say, all the clips where a specific sound occurs, like a siren. This AI could potentially scan and pinpoint those moments automatically.
Or the other way around, if I have a visual of something.
Exactly. You have a visual of a door opening, it could find the corresponding sound clip. It could just drastically speed up finding relevant media.
That would be huge for anyone working with lots of video and audio, a real game changer.
Absolutely. And zooming out a bit, the researchers suggest this could seriously enhance how robots perceive their surroundings. Well, our world is full of both sights and sounds, right? For robots to navigate and interact effectively, especially in complex dynamic places, they need to process both seamlessly.
And currently, we'd have to program every single sound object link.
Pretty much. Or rely on simpler methods. This kind of learning could let them build that understanding more naturally, more like we do.
Okay, so CAV-MAE Sync is the new kid on the block, but you mentioned it builds on earlier work, CAV-AA.
That's right. CAV-MAE Sync is an evolution. The original was just CAV-MAE, which stands for Contrastive Audio-Visual Masked Autoencoder.
Quite a mouthful.
It is. But the basic idea behind CAV-MAE was already pretty neat. You feed it unlabeled video clips.
Okay.
It then encodes both the audio and the visual data into these digital summaries. They call them tokens.
Like representations.
Exactly. Separate tokens for audio, separate for visuals. The key part was it learned to map the corresponding audio and visual tokens closer together in its internal understanding, simply by noticing they occurred together in the video.
Ah, so learning by association. If the sound and the image happen at the same time, the AI assumes they're related.
Precisely. And to make the learning even stronger, CAV-MAE also used this technique called masked autoencoding.
Masked autoencoding.
Yeah, it would randomly hide parts of the audio data and parts of the video data. Then it would try to reconstruct or guess what was missing based on the context of the parts it could see and hear.
Oh, like filling in the blanks in a sentence.
Exactly. It forces the model to develop a deeper understanding of both the audio patterns and the visual patterns, not just superficial links.
Okay, that sounds clever. So CAV-MAE laid some important groundwork. What were its limitations then? Why did they need CAV-MAE sync?
The main issue came down to timing. The granularity of the alignment.
Granularity.
Yeah, how precisely it could link a sound to a visual moment. CAV-MAE tended to treat relatively long chunks of audio, maybe 10 seconds, as a single unit.
10 seconds is quite long in video terms.
It is. And that made it hard to precisely link a specific short sound within that 10-second clip to the exact visual moment it happened.
Ah, I see. Like the MIT news example you mentioned, the door slam.
Exactly that. A quick sound, like a door slamming, maybe half a second, could get lost or averaged out within that broader 10-second audio chunk. CAV-MAE might just associate that whole 10 seconds of sound with one representative video frame.
So if you wanted to find the exact frame where the door visually closed based on hearing the slam, CAV-MAE might struggle.
It wouldn't be very accurate, no. And that's where the key innovations of CAV-MAE sync really shine. They focus specifically on getting much, much more precise temporal alignment.
Okay, so how did they crack that timing problem? What's the fix?
Well, the first major step was to break down the audio. Instead of processing a whole 10-second recording at once,
Yeah.
CAV-MAE sync extracts much smaller audio segments, tiny snippets really, that correspond more closely to individual video frames.
So like matching a tiny bit of sound to each picture in the video sequence?
Pretty much. They align them based on their timing. If a video frame happens at, say, 3.2 seconds, they grab the audio right around that 3.2 second mark.
The MIT news article mentions speech and a toot sound example. How does this finer-grained approach help there?
Right, so imagine that short video, someone's talking, then suddenly a car horn toots.
Okay.
With the original CAV-MAE, the whole audio mix talking then toot might get linked generally to the video frames. But with CAV-MAE sync, because it's using these small aligned segments, it learns separate representations for the talking sound that align specifically with the frames where the person's mouth is moving, and a distinct representation for the toot sound that aligns with the frames where you might, see the car or just when the sound occurred.
So it isolates the sounds in time much better.
Exactly. It gives a much clearer picture of what sound happened when visually. It's like zooming way in on the audio timeline and matching it frame by frame.
That makes a lot of sense. Okay, so better timing through smaller audio chunks. What was the other key improvement?
The other big idea was about how the model learns internally. They realized the original CAV-MAE was trying to juggle two slightly different jobs, using the same set of tools, the same internal representations.
Two jobs.
Yeah. Job one was that contrastive learning part associating similar audio and visual data, figuring out this sound goes with this image.
Okay.
Job two was the masked autoencoder part, reconstructing the missing bits of audio and video, filling in them.
And doing both with the same representation was problematic.
It could cause conflicts, yeah. Like trying to focus on two different puzzles simultaneously using the same pieces. The model might end up compromising, not being quite optimal at either task.
So how did CAV-MAE sync address that?
They introduced something called global tokens. Think of these as specialized representatives.
Okay.
Their only job is to focus on that contrastive learning task, figuring out the overall audio-visual connection. Do these generally go together?
So they handle the high-level matching?
Exactly. And that frees up the regular tokens, the ones representing those small audio-video patches, called patch tokens, to focus purely on the reconstruction job, filling in the missing details.
It's like having dedicated teams for different responsibilities within the model.
That's a great way to think about it. Specialization.
And the paper also mentioned register tokens. What do? Are they another team?
Sort of. The research paper explains that these register tokens act kind of like helpers. They help take some of the general processing load, some of the basic semantic meaning off the patch tokens.
Okay. Why is that helpful?
Imagine the patch tokens were trying to capture both really fine-grained details and some more general contextual information. The register tokens step in to handle some of that broader context.
So the patch tokens can really zero in on specifics.
Exactly. It allows those patch tokens to become even better specialized for capturing the precise details needed for that fine-grained audio-visual alignment, and importantly for figuring out where a sound is coming from in the video, the localization part.
Okay, wow. So smaller audio segments for timing, specialized global tokens for matching, patch tokens for details, and register tokens helping out. It sounds quite intricate. How does the model actually learn with all this going on?
The training process still relies on those unlabeled video clips.
Yeah.
That's fundamental.
Right, no human labels.
The model takes a video, breaks the audio into those small frame-aligned chunks, and then randomly hides masks parts of both the audio and the video data.
The fill-in-the-blanks part.
Exactly. Then it pursues those two main goals we talked about. First, using the global tokens, it tries to learn which overall audio and visual clips are related, the contrastive part.
And second?
Second, using the patch tokens, helped by the register tokens, it tries to predict and reconstruct those hidden or masked parts of the audio and video.
And it just gets better by trying.
It gets better by constantly trying to minimize its errors on both tasks. It adjusts its internal connections to make better predictions and better associations over time.
How do they make sure it doesn't just focus on one goal and ignore the other? Like, only get good at reconstruction, but not association?
Ah, good question. They use a balancing act during training. They essentially assign weights or importance levels to each objective, the contrastive loss and the reconstruction loss.
Okay.
By carefully tuning these weights, they ensure the model pays sufficient attention to both learning to link related audio-video and learning the detailed structure within each modality.
All right, so the model is trained up. How do we actually know if it's any good? What kind of tests did they run?
They put it through its paces on several standard benchmarks, standard data sets used in this field, things like VGG sound, audio set, and one called 8020K sound.
And what did they test on those data sets?
They evaluated it on what are called downstream tasks. These are practical tests designed to see how well the learned audio-visual representations actually work for real-world type problems.
Okay, like give us some examples.
So one key task was zero-shot audio-visual retrieval.
Zero shot, meaning it hasn't seen that specific pairing before.
Exactly. Can the model find the correct audio clip for a given image, or the right image for a given sound, even if it wasn't explicitly trained on that exact dog breed barking or that specific musical instrument?
And how did it do?
The results were really strong. CAV-MAE sync significantly outperformed previous models on this retrieval task. That includes their own earlier CAV-MAE, but also other well-known models like ImageBind and AVZAM.
So better at matching sights and sounds it hasn't encountered together before, that definitely suggests it's learned a more general understanding.
It does. That's a good sign. They also tested it on classification tasks.
Like identifying what's happening.
Yeah. Predicting the action or the sound category in an audiovisual scene. Is it a dog barking? Is someone playing a guitar? That kind of thing. Again, strong performance.
Okay. And you mentioned another one, something about segmentation.
Right, maybe the most interesting one. Sound-prompted semantic segmentation.
Sounds complex. Break that down for us.
Okay, think of it like this. You give the model an audio clip, maybe the sound of someone writing on a blackboard.
Okay. Chalk squeaking?
Yeah, that sound. Then you also give it an image that contains a blackboard, along with other things. The model's task is to highlight the pixels in the image that correspond to the sound source.
So it has to find the blackboard in the picture just by hearing the sound of writing?
Precisely. It generates a kind of heat map over the image, showing where it thinks the sound is coming from.
Wow.
They used the 80E20K sound dataset for this. The paper shows some really impressive visualizations, accurately locating blackboards from writing sounds, roller coasters from their rumbling noise, even airplanes based on engine sounds.
That's incredible. It's not just recognizing airplane sound, it's saying the sound is coming from that specific area in the image. That feels like a much deeper level of understanding.
It really is. It's linking sound not just to an object category, but to a spatial location within a visual scene. And notably, the researchers point out that CAV-MAE sync achieved these strong results across the board, often doing better than more complex methods, even sometimes with less training data.
Okay, so the results look good. To really understand why it works so well, did the researchers kind of take it apart, figure out which pieces were most important?
They did exactly that. Standard practice in this kind of research is to run ablation studies.
Ablation, like removal.
Exactly. They systematically remove or change different components of their model, like the global tokens, or the way they segment the audio and then rerun the tests to see how performance changes. It helps pinpoint which innovations are actually making the difference.
Like figuring out which ingredient in a recipe is crucial by trying versions without it. So what did these ablation studies reveal?
A few interesting things. One was confirmation that using those shorter audio segments they found, around 3 to 4 seconds, worked well, was indeed more effective for temporal alignment than the longer 10-second segments used previously.
So shorter is better for timing.
It seems so, which could also mean more efficient processing, potentially. They also found that, perhaps unsurprisingly, using more video frames during training and tucking what they call denser temporal sampling led to better results.
More visual data points helps it learn the connections better. Makes sense.
Definitely. And they really hammered home the importance of those global tokens.
The ones for the high-level matching.
Yes. When they removed those, they saw a clear drop in performance, especially for the cross-modal retrieval task, finding audio from video or vice versa, but also for localization and classification. It really underscored the value of having that dedicated mechanism for the contrastive objective.
So separating the learning goals really paid off.
It seems so. They also played around with the masking ratio, how much data to hide during training. They found a sweet spot, around 75% masking, gave a good balance between retrieval and localization performance. Too much or too little wasn't as effective overall.
Fascinating. Okay, pulling it all together then. What are the big takeaways, the real-world implications, and maybe where does this research head next?
Well, to reiterate, the potential applications in content creation, think automatic video, audio searching, tagging, maybe even editing assistance, seem pretty significant.
And robotics, too.
In robotics, definitely. Giving robots a richer, more integrated sense of hearing and sight to understand and navigate complex environments. Imagine robots that don't just see an object fall, but can also hear the thud and react more appropriately based on both senses.
It's like giving AI a more complete, more human-like perception of the world around it.
That's a good way to put it. And the researchers aren't stopping here. They explicitly mention a future goal, integrating text data into this framework.
Ah, so sight, sound, and language.
Exactly. The aim is to build truly multimodal models, perhaps even large audio-visual language models. Think about an AI that could understand context, generate descriptions, or even create content based on integrating information from vision, audio, and text.
Yeah.
The possibilities there are really vast.
And thinking about the listener, you. Imagine AI helping automatically organize your own photo and video library. Not just based on faces or locations, but maybe grouping clips based on the sounds happening. Laughter, music, conversation.
Or robots in your home or workplace. They can understand nuances, not just seeing a door as ajar, but hearing the creak that tells them it's opening slowly.
So if you had to sum it all up for us, what's the core message here?
I think the key takeaway is that this model, CAV-MAE Sync, represents a really significant step forward. It's pushing AI towards understanding the world more like we do, naturally connecting sight and sound without needing explicit labels for everything.
And the key innovations were?
Focusing on that much finer-grained temporal alignment, getting the timing right between audio snippets and video frames, and cleverly disentangling the learning objectives using those specialized tokens. It led to impressive results, often with a simpler approach, and it really opens up exciting avenues for the future.
Definitely something to chew on. Think about it. How might this kind of technology change the way you interact with digital media or even the physical world in the coming years? What things that currently need our human ability to link sight and sound could be automated or enhanced by AI like this?
It's a powerful question. And if this deep dive into how AI is learning to see and hear together has sparked your curiosity, remember you can explore the fundamentals of AI much further. Check out the comprehensive course over at rajamanikam.com.
Right, and don't forget that discount code QPT for a special offer at checkout.
Definitely use that. Thanks for diving deep with us today.